Okay, so if our fluid behaves as a continuum, so that we have fluid extending from one boundary to the other boundary, right up to the edges of the walls, then at any point in that continuum, any point in space, two-dimensional or three-dimensional space, that little element of fluid will have a particular velocity. And we can write it as a U with a little arrow on top like that, or as is used in Munson typically and some other textbooks, we can write it as a capital V, bold-faced, usually with some serifs on it, also indicating that it's a vector. But the key thing is velocity at any given point in the fluid is a vector in either 2 or 3 dimensions. Now if we want to look at this vector, we can break it down into components. It'll have some going in one of the primary Cartesian directions, some component going in another of the Cartesian directions, some component going in the third Cartesian direction. So we can break it down into 3 components. Might be this part, and that part, breaking out the components. So if we're looking at a two-dimensional coordinate system, for a two-dimensional flow, we'll typically make that x and this y. We have unit vectors I in the x direction and j in the y direction, and we'll write our velocity, either a lowercase u with an arrow or an uppercase bold-faced V, as equal to a component in the x direction, so some value times the unit vector in the x direction, plus a component in the y direction, some value v times j, the unit vector in the y direction. So to some extent the velocity goes in this direction, to some extent it goes in that direction, so that if we had this is our velocity vector, then that value there is u in the x direction, and the magnitude of that component of the vector in that direction is v. If we have 3 dimensions, looking something more like this, typically this will be y, x, and z in the vertical direction by convention. We'll have a unit vector k in the z direction, still j in the y direction, and I in the x direction, and u will be equal to, again, same thing if we write it as an uppercase V bolded, they're both velocity vectors. The u component in the x direction plus the v component in the y direction, so times the j vector, plus a w component in the z direction, so times the k vector. So two-dimensional arrangement or a three-dimensional arrangement, depending on what type of a system we're trying to look at. And each of these are components. So that's the x component. Here's the y component, the v, and that's the z component. And we can conserve momentum in each of the 3 different cardinal Cartesian directions separately.